Welcome to the ChemDoctor, and the main purpose of this presentation will be to define and describe the concept of isotope. So at the beginning of any kind of chemistry class, whether it's the university level or whether it's at the high school level, generally speaking, you're going to start with the concept of the atom. And we know that the atom is composed of three basic subatomic particles: the protons, the neutrons, and the electrons. Now, this is 2014, and most of you are going to be sitting there going, okay, well, we know that those particular subatomic particles can also be broken down into smaller particles. And yes, that's true. However, in most basic chemistry classes, we're not going to be concerned with subatomic particles that are smaller than protons, neutrons, or electrons, because the chemistry that we're studying is what we would call macroscopic. What we want to learn about to just understand the basics of chemistry are the physical and chemical properties of the elements, how they fit together to make molecules, and how molecules can be fit together to produce things that are bigger. All right, and so we're not concerned on the nuclear level with things that are smaller than the protons and neutrons. Now, with that said, generally the professor will start with a short description, perhaps of the history of chemistry. More than likely, Dalton's atomic theory is going to come up, and Dalton was one of the first scientists to suggest that atoms are the smallest unit of matter. Now, we know that that's not true, but again, what we're going to do in most of these courses is assume that this is true in order to describe the more macroscopic physical and chemical properties of the elements. And so very quickly, the concept of isotope usually is addressed in these classes and glossed over very quickly, and in my experience, I have found that most students don't really get what the concept is. So what I want to utilize this presentation for, and you'll also find other videos on my website that deal with the concept isotope, but in this presentation, I basically want to hammer the concept home. So we're going to focus on a particular element called lithium. If we extract its box out of the periodic table, you'll notice that there are two numbers above and below the symbol. The number above this of the atomic symbol is called the atomic number. Hopefully remember or recall that the atomic number gives you the number of protons. Why is this important? Because a particular element or a particular atom has a designated number of protons in it. So the only element in the periodic table with 3 protons is lithium. And if you're dealing with anything that has a different number other than 3, then it can't be lithium. So lithium is the only element on the periodic table that's going to have 3 protons. This number at the bottom, and I'll use a different coloration to indicate that one, is called the atomic mass. And I'm going to come back to that concept near the end of the video. But essentially, the atomic mass is a weighted average. Because as it turns out, even though we learned at the beginning of these classes, in fact, I would be willing to put money on this, the professor's going to tell you that all of the atoms of a particular element have identical physical and chemical properties. Well, in at least one respect, this is a lie. Because as it turns out, not all the atoms of a particular element have exactly identical properties. And one of the properties that can be different is mass. So let's see how this works. If I went out into nature, and again, I'm going to take certain liberties here because you're not going to find elemental lithium sitting around on the surface of our planet. It's not stable. You're going to find it in the form of salt. However, for pretend, let's say that we could go out into nature and collect elemental lithium, and we would bring this sample into our home and we would crush it up. And essentially, we would take randomly 100 atoms out of that sample. And I'm going to write that down up here, 100 of those atoms. And we would spread them out on a table. And what we're going to find in that sample of 100 atoms is essentially there are going to be 2 types. All right, one of the types and I'll do this quickly here, is going in the nucleus we'll have a total of 1, 2, 3, 6 particles. The other sample, or the other type of atom that you're going to find in that sample of 100, 1, 2, 3, is going to have a total of 7 particles in the nucleus. 1, 2, 3, 4, 5, 6, 7. Okay, and I'm going to define for us over here, these spheres are going to be of 2 types. So we're going to use the open circles as being the protons. Remember, the protons define the identity of the element. So 3 of these circles are, in both cases, are going to represent the protons. And the other one that we're going to go ahead and fill the sphere up. Right? And these represent neutrons. So we're going to see in this sample of 100 lithium atoms that the 2 of them can have different numbers of neutrons. This is in fact the definition of an isotope. So for this guy here, I'm going to go ahead and fill in 3 of them. And this guy over here, we're going to fill in 4 of them. All right, and we need to address the electrons because every atom has got electrons. So I'm just going to arbitrarily draw an electron cloud like this over here. And the focus of this presentation is not on the electrons, so I'm not even going to draw them in, although there would be 3 of them for lithium total. So this is just an arbitrary electron cloud where we would find the electrons. All right, so I'll just do this going around. The main thing to see here is that out of this 100 atoms, out of this 100 lithium atoms, there are going to be 2 types that we find here. Both of them have identical numbers of protons. They have to if it's lithium. On the other hand, you see that they can have different numbers of neutrons. This means that in a sample of 100 atoms, there are going to be mass differences. I'm going to emphasize that here, mass differences. And put that underneath my formal definition of a neutron. I mean, of an isotope, excuse me. All right, now, we're going to symbolize these 2 things a couple of different ways. One way that we can describe the isotopes of a particular element is this way. So we write the atomic symbol, we have a hyphen, and then we write this number. And in this case, we're going to use the number 6. For this one over here, we're going to use the number 7. What are these 2 numbers? All right, so we need to define a new concept here. And that concept is mass number. Now, mass number is not the same thing. It is not atomic mass. The students mess this up all the time. So what is mass number? It is the number of protons plus the number of neutrons, literally. So we see that for Li6, there are 3 protons, which there have to be if it's lithium, and then we've got 3 neutrons in this one. In this particular atom of lithium here, we've got, again, the 3 protons, but then we have 4 neutrons. All right? And we also can represent this using what's called AZE notation. So again, we write the symbol. All right, and in this case, we're going to write the actual mass number in the upper left-hand corner. So we would write 6 for this one and 7 for this one. And in the lower left-hand corner, we're going to write the atomic number of the element. So 3 goes in this spot and 3 in this spot, like that. This would be what we call the AZE notation for these 2 isotopes. Now, out of the 100 atoms, lithium-6 and lithium-7 are not present in the same amounts. All right? For lithium-6, and I've rounded these numbers in order to make this presentation simplistic, all right? But for lithium-6, this represents about 7% of the sample. And for lithium-7, this represents about 93%. Now, these percentages represent what we call percent abundance. This is the percent that you're going to find the two elements when you look at a random sample of the material found in nature. All right, so we've got about 93% of these atoms are going to be lithium-7. So how does that boil down to in terms of our description? Well, I chose an easy number. We're going to say that we've got 100 atoms spread out on our table. And that means out of those 100 atoms, you would expect to find about 7 of those atoms are going to have 3 neutrons, and about 93 of those atoms are going to have 4 neutrons. So let's go ahead and add that into our information here. So this sample is going to be composed of 3 neutrons, and this sample is going to have 93 of these atoms are going to have 4 neutrons. So the question is, to finish the video, how do we relate mass number to this concept of atomic mass? All right. So, and again, at the beginning of the presentation, I said atomic mass is a weighted average. So how's this going to work? So our atomic mass is going to will represent the sum of the two types of atoms, accounting for the sum of the masses of the two types of atoms, accounting for their percent differences in the sample. Now, for the lithium-6, its atomic mass is 6.015122. All right, and for the lithium-7, its atomic mass is about 7.016004. All right, you can look these up on the internet, and you may find slightly different numbers depending on the site, but this is what I found. All right, now to find the atomic mass, what we're going to do is take the atomic mass of the individual isotopes multiplied by their percent abundance, or the fractional percentage, summed together. So for the lithium-7, it's going to be 7.016 and change times its percent abundance, which is 0.93. All right, and when you add this together, you should get a number that's going to be very close to the reported atomic mass of, it should be approximately 6.941. But remember that I rounded some things here. My main point is to describe to you how we arrive at the atomic mass. All right, and with that, I'm going to go ahead and close the presentation.